Okay, so semiconductors. Now what I'm going to do is I'm going to pause the video whilst I draw and do the next bit and see what it looks like. It might look really weird that I like jerk a bit and stuff, but then I've been called worse things in my life than a jerk. So semiconductors. Okay, semiconductors are between conductors and insulators. Remember, let's go back to free charge carrier density, or little letter N. Okay, so free charge carrier density here, little n, which was in the drift equation, drift velocity equation. It's how many free charge carriers we have in a material, in a substance, per cubic meter. So this number is usually mega massive. Like in conductors, in a metal, we're talking about somewhere around the region of times 10 to the power of 28. So that's million, billion, billions per cubic meter of metal. Okay. Now, if we have an insulator, we could be close to pretty much zero free charge carriers. There's no charge carriers free to move around in plastics, for example, or in ceramics. Okay, so number of free charge carriers in insulators is going to be pretty close to zero. So semiconductors are somewhere there around the middle-ish. Okay, silicon is around 1 times 10 to the power of 10. Germanium is about 2 times 10 to the power of 13. But these are like the approximate ballpark figures that we're talking about. Okay, now why are semiconductors interesting? Now, we can use them for lots of different things, but we need to think about the structure of the semiconductor. Now, remember the structure of a metal conductor. We have lots of free charge carriers in the metal conductor, in between the lattice of metal ions or metal atoms. Okay, so all these free charge carriers, these free electrons, are free to move around in the metal and hence carry current as they flow through the metal in between the metal atoms. And in a metal, if you increase the temperature, because the temperature means that these atoms vibrate more, there's more movement of these atoms side to side, then there's more likelihood of the electrons colliding with the metal atoms or the metal ions. And more chances of collisions means more resistance. So as temperature increases in a metal, resistance also increases. Right? Now, I'm going to pause for a second whilst I draw something. Okay, so this being a semiconductor, I'm going to just have one solitary electron there that is free to carry charge through the semiconductor. All right. So having a low number of free charge carriers means that the resistance of this semiconductor is quite high. Okay. Now, here's the thing. With the semiconductors, all the electrons are locked away in bonds between the atoms. Okay, so these atoms, these silicon atoms, are sharing electrons. So electrons are not free to go anywhere because they're bound to the atoms. Now, what can happen is maybe it's increasing temperature, or maybe it could be a photon of light, electromagnetic radiation. A photon strikes the semiconductor, so either heat vibrations in the atom, the ion lattice, or a photon strikes the semiconductor, and that addition of energy can free up another electron from its atom. So this is what happens. So could be heat, could be a photon's energy that's freed up the electron. So now, all of a sudden, I have another free electron here that has come from this atom down here. Okay, so I've gained a free charge carrier, which, seeing as there's not a lot of free charge carriers available, that's going to make a big difference, a big reduction in resistance. I'm going to have just a few additional free charge carriers, makes a big difference. Now, what's also happened is that that electron that's been freed up has left behind a positively charged ion. Now, if I put a potential difference and I start to get this current flowing through the semiconductor, give me a second for that. There we go. So now I've got a current. I put positive and a negative. So current's going from positive to negative, which means of course the electrons are drifting away in the opposite direction. So electrons are drifting, oh my god, this is really that away. Okay, so electrons are going that way because the current's going that way. What's going to happen here is this positive ion that I've got freed up down here, okay, I can have an electron jumping from the neighbouring atom, okay, and this is an electron that's bound up to that atom. It's forming part of the covalent bonds with the neighbouring atoms, but an electron that's not free, it's not a free charge carrier, it's not free to move about, but it can pop from this atom to this one. So let me just add that effect on to the bottom as well. Give me a second. So what could happen here is an electron that is not free, it's not a free charge carrier, has jumped from this atom, to the positive ion. So these are not free charge carriers, but the electron has jumped from here to here. The visible effect of this is we'll see that a positive ion, this will no longer be a positive ion because it's gained one of the electrons from the neighbouring atoms. So that positive ion won't be there anymore. The positive ion will be here. So that positive charge will jump from there to there. And we refer to this as a positive hole. So the positive charge in the lattice has jumped from there, made a jump to there. So I do get more free charge carriers in the silicon lattice. Free charge carriers are carrying the current in that direction. Whoop. That away. But then the effect of freeing up this electron means that this positive hole in the lattice, positive hole, because it doesn't really exist, it's the lack of an electron in the lattice. So that the positive hole caused by the lack of an electron will move that way, it will jump one place that way. So I can actually get the positive charge moving in the opposite direction, and that can carry charge around the circuit as well. So I get one more free charge carrier that carries the charge that way, and I get a positive hole that's carrying the charge that way. So if we're freeing up just a few electrons in the lattice, I get actually a big increase in the amount of charge or the amount of current that can be carried by the silicon, and hence I get a reduction in resistance, which is what brings me to what thermistors and what light dependent resistors do. As temperature increases and vibrations in the silicon lattice increase, this frees up more electrons and more positive holes, so it reduces resistance. So as temperature increases, resistance decreases, and this is what we call negative temperature coefficient, because as temperature increases, resistance decreases. It also happens in light dependent resistors. As we get more photons striking the silicon, we get more electrons freed up and more positive holes. So greater light intensity means more free charge carriers, and hence reduction in resistance. So in thermistors we call it negative temperature coefficient thermistors, NTC. Thermistor, or a light dependent resistor, and if we plot for both of these temperature against resistance, so I vary temperature put it on the x-axis. Measure resistance, put it on the y-axis. Get a relationship like this, okay? Negative correlation, but I don't get a linear relationship because for each free charge carrier that's freed up, we also get a positive hole. So the relationship is not linear. Don't need to go and talk about exponentials or things like that. No. Don't need to go there. You just need to say that it's not linear relationship. It's not a linear. Same with light dependent resistor. This is a thermistor. Light dependent resistor, LDR. As light intensity increases, resistance will decrease in a similar way. Similar relationship for light dependent resistor, which we'll have a look at that experiment quickly now. Light dependent resistor, draw like this. Circle resistor and two arrows going into it. Thermistor is a resistor with a hockey stick across it. Okay, and that's semiconductors. The only thing we need to do more about semiconductors is experiment with light dependent resistor, where we'll also look at intensity of the light and distance, and we also need to talk about doping. Sounds good. Doping the semiconductors, and I will do another experiment to explain because I've been asked about the potential divider or potentiometer. Okay, and then we'll get cracking on with past papers and paper 3 preparation. Okay.